Hi guys, it's Mr. Robeson here again. We are working through AP Statistics, and today we are looking at the end of Unit 9, Hypothesis Test for the difference of two population means. We're just going to look at what the test is and a couple examples. All right, so again, with all of our tests, all of our procedures, we're doing state, plan, do, conclude. I kind of separated into two slides here, but we've got our state, where we state what each mean stands for. They don't have to be mu sub 1 and mu sub 2, but you can use that if you want. But it should always start with the true mean and then say what context it is. Same with mu2, same thing, true mean, and so on. All right, our null hypothesis. So we can go with the difference equals 0, but that is the same thing as mu1 equals mu2, which is usually what we go with. Sometimes it's like less than or equal to, or sometimes the difference is like an actual number, like you can actually equal a number here, but that's okay. Again, we can just write that the difference equals a number, that's fine. All right, for the alternative hypothesis, most of the time it's just one of them is greater than the other one. Sometimes they're not equal to each other, but sometimes it could be that like if the difference was equal to a number, then we would say for the alternative is that like mu1 minus mu2 is less than that number or greater than that number or equal or not equal to that number. All right, so keep an eye out for that. State your alpha value. Usually if we don't know it, we'll just go with 0.05 and list any known statistics. So like if we have like the mean, the sample mean, like x bar 1 or s1 or n1 for the sample size, or x bar 2 or s2 or n2 for our sample size, we can list those there. All right, if we have data, we'll end up listing it down in the do section. All right, the name of our test, so we always want to state our name here for when we're planning for it, is a two sample. We're working with means, so it's t-test. Again, ZapTax helps us out here. We're working with x bar, so we're using t's. Test, it is a test. We're doing a hypothesis test for the difference of two means. You can also say equal to each other, whatever. That should be fine. As long as you have two m's over there, that's fine. Not x bars, always mu's. All right. We need independent random samples. So usually we're coming from two different populations when we do this, so that's generally not a problem, or two different time periods, which also not a problem. All right, we need our normal sampling distribution. So either we need normal populations, like plural, one of each, or sample size greater than 30, the central limit theorem kicks in, which we usually just say is CLT. Or if we're less than 30, we need to look at the graph, and it needs to be not strongly skewed and no outliers. All right, and any combination of these two works. So like we could have one sample is 35, one sample is 25, and one of them we have to look at the graph. The other one, the central limit theorem helps us out. Any combination is fine there too. For independence, same as we always do, our sample size needs to be less than 10% of the population for each one of our samples. All right, doing. So when we get to our calculator, it is a two sample t-test. Two sample t-test. All right, so if we're using data, we put in the lists. If we're using stats, we put in the actual numbers. Generally, we're going to select no if it asks if we want to do pooled data. Unless it says otherwise, we just go with no. All right, and then we write down everything it gives us. So we need the p-value, we need our t, we need our degrees of freedom. All right, if we use data, then we'll write down the sample means, the standard deviation, and the n. Otherwise, we've already listed them. We should be okay. And then we conclude, if p is low, reject the hoe. All right, that still holds. That's been holding basically all semester here. All right, if it's greater than or equal to alpha, we fail to reject. And then we write about our alternative hypothesis. So this is all about our null hypothesis. This is all about our alternative down here. So we have evidence for the alternative, or we do not have evidence for the alternative. All right, make sure we somewhere in there talk about the true mean or the difference in true means, something along those lines. All right, an example. So the mean number of hours Americans work in a week has it changed? One of the questions of the General Social Survey, or the GSS, asks respondents how many hours they work each week. Respondents from random samples, there it is, of employed Americans were recorded from 1975 to 2014 and are summarized in the chart. So we've got 1975 data, we've got 2014 data. Do these data values give convincing evidence at the alpha equals 0.05 significance level of a difference in the true mean number of hours worked? So that's what we're looking at, the true mean numbers of hours worked per week. All right, so we go ahead and we just draw our cross here. All right, and let's see, we're going to have the mean from say 75. So we could say mean 1975, or we could call it mean 1 if we want. But this would be the true mean hours worked per week in 1975, and then we'd have the mean of 2014 equal the true mean hours worked per week in 2014. All right, our null hypothesis is going to be that they're the same. So the mean hours worked in 1975 equals the true mean hours worked in 2014. Our alternative is we just want to see, are they different? So the mean in 1975, is it not equal to the mean in 2014? And our alpha is 0.05. Now, I would say we write down all the stuff, but they already gave it to us in a chart. I don't know if we really need to write it down again. If it's up here in the chart, like this would be the X bar for 1975. This would be X bar for 2014. This would be S for 1975. This would be S for 2014. Oops, I'm off by a oopsies. This would be X bar for 1975. This is X bar for 2014. It helps to read the top of the chart here. This is S for 1975. This is S for 2014. And this is N for 1975. And this is N for 2014. All right. Now, let's see. The name of the test we want to do is a 2-sample. We're working with means, so it's a t-test. We're doing a hypothesis test, so it's a test and not an interval for the difference of means. So mean 1 minus mean 2. All right, that's the name of the test, so we don't have to have these numbers in here. It's just the name of the test. All right, we do have independent random samples. All right, so they're from different years. The different years gets us the independent. The random, we were told up here that it was random. We're good. For the normal sampling distribution, one of our n's, so n 1975 is 764, which is clearly greater than 30, and n 2014 is 1501, also well above 30. So by CLT, we've got an approximately normal sampling distribution. So that checks out. And independence, that should be okay there. All right, so we've got 764 is less than 10% of all 1975 workers. And 1501 is less than 10% of all 2014 workers. All right, we should have millions of workers, so we should be good there. All right, so check. All right, so all the conditions work out. So now we're going to go to the calculator, and it's a 2-sample t test. Was that it? Let me look from the calculator and see if that was the name of it. So on, let's see, we're not in list, stat, tests, 2-sample z, 2-sample t-test. Yep, that's what we're working with, 2-sample t-test. Yep, that's it. All right, we have statistics. We're not using lists. And let's see. So our original mean, we'll say this is all 1, and we'll say the second row is all 2. So our original mean is 38.97 hours per week. And the standard deviation for that one is 13.13. And the sample size is 764. Big sample size for means. The next one, we've got 41.91 hours worked per week. And then we've got a standard deviation of 14.35. So the standard deviation is a little bigger there too. And 1501 is that. And we want not equal to each other. We want to see if they're different. That was our null hypothesis, or our alternative hypothesis, sorry. And there we go, calculate. Oh boy. Negative 4.88 for our t. That's pretty far away from the mean of 0 there. And our p-value is 1.16 times 10 to the negative 6. So remember, if it starts with 1, you look at the end of it, it's in scientific notation. So our p-value, and if it's in scientific notation, it's always going to be really small. All right, and our degrees of freedom is 1660. So we should probably write that down. Degrees of freedom is 1660.8 and so on, or 0.58. And the other stuff we all have, so it just gives us all of our means and standard deviations and ends again. So we already have all that. All right, so this is really low. All right, so this would be 0.123451116, like that. So since p, our p-value is 1.16 times 10 to the negative 6th, is less than our alpha value for sure, we reject our HO. That's the mean in 1975 is equal to the mean in 2014. So that means we have significant evidence that the true mean hours worked in 2014 is different or is not equal from the true mean hours worked in 1975, different from, I'm going to say it, in 1975, because I don't know if I have enough room to say the true mean hours worked in 1975. All right, so there we go. That's how we do our hypothesis test for 2 samples when we're working with means. And that's how we do it if it's a free response. We want to draw our boxes and fill in all of our boxes. If it's a multiple choice, we don't have to do all that. All right, so we can kind of do the shortcut if we want, just do the calculator part. So to determine if the drive-through is faster than going inside of Wendy's, researchers went to Wendy's 70 times throughout the week and flipped a coin to determine, so we got randomization right there, if they would go inside an order or go through the drive-through. The time it took to get their orders, the same order each time, Baconator, of course, was recorded in seconds. Based on the data below, is there significant evidence at alpha equals 0.05 level of a faster drive-through time? All right, so let's see. Our null hypothesis would be that the mean time in the drive-through, let's say dt, is equal to the mean time inside. Our alternative hypothesis is that the mean time in the drive-through is faster, so that'd be less than the mean time for the inside. So that might be helpful to write those down. So we'll call this our x bar 1 and S1, and this will be x bar 2 and S2. So this would be like mean 1, this would be mean 2. That's, I mean, those guys. And this is N1, and this is N2. All right, so we can go straight to the calculator. Like, we can check all the conditions if we want. Like, our sample sizes are both over 30, so we've got the normal thing going for us there by the CLT. Independence, we could go to the drive-through as many times as we want, so we don't have to worry about that. Random samples, we flip the coin to determine which one we're doing, so that does randomize our samples. And let's see, so we really just want to do a 2-sample t-test on our calculator to see what we get for our p-value. So we pull up our calculator, and let's see, stat, test, 2-sample t-test is number 4 there. And we're using stats. We got a lot of numbers to put in here. So our mean for the drive-through is 105.3 and 21.4 seconds for standard deviation with a sample size of 38. So these are more reasonable sample sizes compared to last time. The next one, we've got 112.5 and 25.3 for standard deviation with a sample size of 32. And we want to know, is M1 less than M2? So there we go, that one. Not pooled. and calculate. So here is our t, here's our p-value, 1.104. So our p-value was 0.104. Oh, that's this guy right here. And that is greater than 0.05, which is our alpha. So we fail to reject our null hypothesis. So that means we're going with this. We're going with that they're equal, so we do not have evidence that the drive-through is faster, or we do not have significant evidence, I guess is the key word. We do have some evidence because this mean is smaller than that mean, but it's not significant. All right. There's our answer there. All right, and that is the end of this section. We do have some more examples with data coming up next, so come back in a second and see the ones with data.